Okay. Okay, so talking about perusal. Yesterday when I went to record scores, I went to the grade setup and it was not showing percentage. Last semester, it just showed me 100% for most people, 97%, 93%. And so I was trying to figure out how to get it to show percent. And so I'm going through the grade book and it has, how are you calculating grade? There's the, we strongly recommend this, or you can do something else. And I was like, well, I think I'm already doing it, but I clicked the we strongly recommend. And it dropped everyone's grades. And I have no idea what happened there as far as why everybody's grades dropped. And so for the short term, I made 2.5 100% just to try to get by while I contact them and try to figure out what's going on and how to get back. Because, you know, I want people to, if they're doing a fair amount, you know, making sure they're not just concentrating on the first 2 pages and their comments are making sense, I want them to get full credit. So I will continue to look into this to try to get things back to where they were. Because I frankly don't know why what I did what it did. Claudia.
Just like a quick heads up, I did 6 annotations, all with like 2, like my average quality was a 2, and my distribution was 5. And with that, I have 2.4.
Yeah, I don't know. I just don't know.
To get it from a 2.4 to a 2.5, you had to go from like 7 comments to 12 comments.
So like,
it doesn't actually count any more than your top. I changed it down to 4 also to try to make sure it raise people's grades.
Okay.
So it's only your top 4 comments. So it's not how many you did, it's just the top 4 of the ones you did.
What? So are you gonna make it less? Or
What I hope to do is get back to where we were. But I have to contact them and try to figure out what happened. And I know there's one student that's sitting at 112% right now that's like, no, really, you don't have to. I don't know why that student has 112% and the rest of you don't. Okay, so you know who it is.
okay, but are we still like in agreement? Because like at the beginning of the semester, we all talked about that it was really like it was so much more time consuming.
Right, that's why I lowered the number of responses that it's counting now.
So what is our number?
It was at 5 after this. I lowered it to 4 in hopes that would raise people's grades.
So like the number that we should shoot for is a 2.5.
Well, I don't know. That's right. I just don't know. I'm giving you everything I have.
So should we just say if you do 4, like at least 4, and they were quality, like you should be okay?
It is, as long as you also space them out.
Okay.
That's my belief.
So that's well.
But I don't know what's going on, so I can't be very exact because I don't know what's going on. David had a question, then back to Sarah, and then we'll start.
Oh, no.
Okay, Sarah?
Because you already put in 2 that after the grade change, can you at least go back and change those to 3s, assuming that...
Well, I don't have any record of what the grades were.
No.
So now we're just screwed?
No.
Well, I hope not. That's why I'm contacting them. Right? I want to get
Can you
things...
take it on faith of what we told you? Like, why wouldn't we not go
You can
to
look
an
at how
100?
many
Yeah, we all got
comments.
Yeah, are you kidding me? Like, why wouldn't we get an 100?
I want the numbers to actually be reflective of something that is verifiable. I don't have any problem trusting people, but it's as a teacher, you have to...
You can go on and look, because the old score was out of 7, correct? It was out of 7 points, right?
And then I think it dropped to 5 because that's my question. So for some of mine, I started only doing 5 comments instead of 7, and we had talked about that in class that you were going to like 5 comments.
Right.
So then for a while there, which is why I think that my grades dropped so low, I was only doing like 5 quality comments because that would get me to a 3.
Mm-hmm.
And so I was like,
and it should.
Okay.
That's the goal.
Wait.
But before I had 7 comments.
The old grading scale was out of 7, right?
Yeah.
It was
What?
the old grading scale.
It was out of 3.
But the old one was
But-
out of 7.
It was out of 7.
It was out
Well,
of 7.
it was...
Last semester.
Yeah, it was... Okay, 7 comments.
It was out of 7 comments. You
Yeah.
lost like 7 total points or something.
I don't know.
Yeah.
It gave a percentage.
It gave a percentage.
Yeah.
Is
And
that
it was
what
out of
you're
7
trying
But
It was out of 7 comments.
let's
7
just-
points.
I will look into this.
Yeah.
I do not want anybody's grade to suffer. right? That is my goal here. My goal is not for people's grades to be down or for people to feel stressed.
Oh, no.
I recognize that. And so my goal is to alleviate that. Okay, review of what we covered last class period. We talked about electric potential. We learned about the electric potential energy and adding them up for multiple points. And then the definition of electric potential as the electric potential energy per charge, and the necessity of always having a reference point. And then at the very end, we talked about the unit of the electron volt, which is just a lazy way of getting units of energy. Today we're going to talk about electric potential for multiple charges and some biological applications, and then we might get into capacitance. So jumping into things, we saw this slide last class period. I want to go back to this picture and make sure we're real clear on this. We have two plates. This one has pluses, so we'd say it has a positive charge. This one has negatives, we'd say it has a negative charge. Electric field lines always go out of positive and into negative. And electric potential is a measurement that tells you about how the energy varies. And so if I had a positive charge, the positive charge would be repelled by positive, attracted to negative. So it'd have a higher potential energy if it's closer to the positive plate. So the positive plate is also the one at a relative positive voltage. The negative plate is at a relative negative voltage. So when you see those pluses and minus, it truly means positive charge and negative charge. But you can also think of that as the positive voltage versus the negative voltage. But keep in mind the voltage is always measured relative to some reference point. So you could have the negative one is at 0 and the positive one is the positive voltage. You could have the negative one is at -5 and the positive one is at +5. Let's just stay with 10 volt differences. 0 and +10, -5 and +5, or it could be 0 and -10, or it could be 310 and 300. The one that is the positive is the higher voltage, the one that's the negative is the lower voltage. Now, a final thing on this is equipotential surfaces. Equipotential surfaces are surfaces where you have the same potential energy. If a charge moves parallel to the electric field, then there's going to be work done on it, so its potential energy is changing. So equipotential surfaces have to be perpendicular to those electric field lines. So whoops, that was not one of them. The equipotential lines would be going like this. I can draw those in just based on it has to be perpendicular to the electric field lines. Okay, so that this electric field points in the direction of decreasing voltage should make more sense in light of what I've drawn here. So sticking with it, this is +5 volts and this is -5 volts. This would be 0 volts in the middle, and this would be maybe plus 2.5 volts and minus 2.5 volts for the lines I drew. Okay, now to the problem that I was going to have you do at the end of last class period. Instead, I will do at the beginning of this class period. A battery-powered lantern is switched on for 5 minutes. During this time, electrons with a total charge of -800 coulombs flow through the lamp. 9,600 joules of electric potential energy is converted to light and heat. Through what potential difference did electrons move? When you read that question, does a method pop out to you? Even to me, the first time I read it, I was like, what? But let's stay with what we have. We have the change in potential energy is 9,600 joules. That's given to us. Andy.
What pops out to me is that potential difference is in joules per coulomb, right?
The potential difference is in joules per coulomb is correct.
And we have joules and coulombs given.
We have joules and coulombs given. That's right.
That's all that pops out to me.
That's a good observation, and in fact, that is all we need to solve this. We have time. Time is 5.0 minutes. It turns out that's unimportant to this problem. We can calculate what we call the current, which you had in your reading for today, I believe, based on that time, but it was not part of what this problem is asking. And then we have the total charge flow. I'm just going to move the coulombs up there. So we have Q is equal to minus 8.0 times 10 to the 2 coulombs. And we're looking for delta V. But the definition of delta V is change in potential energy per unit charge. And so all I have to do is put those two numbers in. And once again, I am not paying attention to the sign. Not paying attention to which side's positive, which side's negative. That's not important to this. 9,600 divided by 800. And you can see that Andy's just paying attention to the units would have worked out perfectly here. Now I have to point out sometimes you have other constants and whatnot. Just looking at units is not, in general, a valid way to solve a problem, but it sure can help you. David.
Why do we not care about signs again?
Why do we not care about the time?
No, signs.
Oh, signs. Oh, because I just wanted to know the voltage difference that this charge went through.
Not if it was a positive
And
difference or a negative difference.
It was negative charge because it was electrons moving, and those electrons are going to move to lower energy if they're giving up energy.
Okay.
And so going to lower energy means they went to higher voltage. And so I can figure out from that which direction the sign is.
Okay.
So just doing that separately. Now, just because it gave us the time, we could have answered a different question. Current. I'm not going to talk about current at all today except for in this problem. Current is the rate at which charge passes. Just like if you have a stream, current is the rate at which water passes. Good.
Sorry, and like the perusal thing,
Uh-huh.
that's exactly what I talked about.
So if I ask for the current here, current has a symbol of I. I don't know why. The current would be measured as the amount of charge that passes per time. So that would be, and once again, I'm not going to put the units, or the sign, 800 coulombs divided by 5 minutes. The standard unit is seconds, so 5 times 60.
300 seconds. That's
1.67 coulombs per second. 2.67. Yes, Claudia.
So in the textbook, it says that I is the change in Q. So what's the difference between?
Okay.
Not a difference at all.
I put Q, I didn't put a delta.
Right.
It's the amount of charge that passes a single location.
So like change in Q or the Q in that location.
It's the Q that passes here. So you didn't have a Q here and now not a Q, or a raising Q or a lowering Q.
Right.
You had a Q that passed by, so that's why I didn't put a delta.
Okay.
But when you get to calculus, you do with a D, and so it's written both ways.
Okay.
And it's kind of a unique definition. That's why.
Right.
Notice the unit here for current is coulombs per second, which we abbreviate to amperes. Something we'll see later, but something you probably already have heard of. 2.67 amps we're passing. And if we combine these definitions, we have delta PE is equal to Q delta V. And so the rate at which energy is passing, right? That's not the energy. The rate at which energy passing would be what we get if we divide both sides by delta T. And so that's called the power. The power is the rate at which energy is being transferred. But if you look at that, we have Q over delta T, which is the current. Q over delta T is the current. And so the power is equal to current times voltage. And then I could have said the energy is power multiplied by time. I could have worked it that way, and I could have used the time, but I would have had to use the time twice. It was an extra work. So I did a bunch of extra things that won't come up in lecture until actually lab tomorrow. Just to give you other insights in how that time might have been useful for a different question, but it wasn't important for this question. And of course, that's something that you have in physics textbooks and physics tests and CAT tests. They will often give you extra variables that aren't part of the problem. There are true things that are going on in the problem, but not part of what you need to solve it. And the reason they do that is not to confuse, but to make sure that you understand how to solve it and aren't just trying to do a problem by the way that Andy said, I see we've got this unit and we need this. They want to make sure that you actually have the process and not just trying to throw them together. Nothing wrong with what you did though, Andy. I'm not. Okay, so that's a first problem. Voltage, going back to voltage or electric potential. For a point charge, we learned that the electric potential is KQ over R, where R is the separation from the charge to where you're calculating the electric potential. Q is the value of the charge, and K is that constant. And if you have multiple charges, you just add them up. So here's a problem, and once again, I'm going to do the problem rather than having you do it, that has you calculate what is the electric potential at A and the electric potential at B due to these three charges. Claudia.
Sorry, was the last slide important? What was the last slide? I was reading it.
Oh, this was just telling you that if you have more than one charge and you want to find the electric potential, you just calculate each one separately and add them up. And this slide is here because that's the method we use to solve this.
Okay, sweet.
So in this problem, I have three charges. And so if I'm going to find the electric potential at point A, I'm simply going to say VA is equal to K, they use capitals here, so K Q1 over R1A plus K Q2 over R2A plus K Q3 over R3A. Now, why did I put R1A? What does R stand for in this case?
Radius. So it's
You think it's radius, but and it is measured that way, but it's separation.
and so that's because for R1, so that's Q1 in this problem, we are 2 units away from A, and it's different. Yeah.
You're doing this one.
Yeah.
Okay, because this was square root of 2.
Right.
But ours, the key is it's the separation between 1 and A. Yeah. So now I can just do the numbers. This would be equal to K, and I'm just going to factor out K from everything. Q1 was 4 microcoulombs over R1 is 2 plus, and then Q2 is 2 microcoulombs over R2, which is root 2, plus Q3 is minus 3 microcoulombs over R3, which is again, well, R, where is it? There it is. That's square root of 1 plus 4, so square root of 5. Whoops. So there I just added up each of the individual voltages. And I'm actually not going to take the time to calculate this. But what I can tell you looking at this is definitely going to be a positive value because I have 4 over 2, that's 2 microcoulombs per, I don't even, the units were centimeters. And then 2 over root 2, that's 0.706. Is that right? No. Yes, it is. 0.706. I have to think about this more carefully. Yeah. For sure it's 0.706. So I have 2 plus 0.706 then minus 3 over root 5. I don't know exactly what that is, but it's somewhere close to 1. Whereas if I did it VB from the same method, and so B to 1 is, that's 2 and 2, that's root 8. Root 2. And that one, I believe, is going to be negative because the 3, I think, is going to dominate the other 2. So it's going from positive voltage at A to a negative voltage at B. But remember, I said voltages are always with respect to some reference point. What reference point are both of these with respect to? I didn't mention it anywhere, right? It's not the origin, it's a point infinitely far away. Whenever you have a point charge, your reference point is by default a point infinitely far away. And then if I want to shift to another point, I can do that. Just I have to know its relationship to that same reference point to do the shift. Now, Anna, you had a question. What was your question?
I just wasn't completely sure what was happening with the bottom numbers, but you were doing it in your head.
Oh, yes. I was doing those in my head. Just this distance here was R1A, which can directly be read. That's the one David was talking about. This here is R2A, which is the square root of 1 squared plus 1 squared. And R3 or R2B is the same thing. And then we have the longer ones. R13 is the square root of 1 squared plus 2 squared. And the final one to do is RB1, which is square root of 2 squared plus 2 squared. So yes, I was doing those in my head. I'm sorry. Yes, I probably should have not done them in my head. Now, the second part, a point charge of minus 5 nanocoulombs moves from a great distance away to point A. What's the key of that great distance away? What possible useful meaning could I draw from that?
None.
No? Our reference point was infinitely far away. So that means it's moving from a place where the potential is 0 to A, where the potential is whatever you get numerically when you do that calculation on top. And then it asks, what's the change in electric potential energy? How do we calculate the change in potential energy? Go ahead, say it. We do what we did in the last slide. And it's the charge multiplied by the change in voltage. So the change in voltage is the final voltage, VA, minus the initial voltage of 0. But if you didn't have this statement from a great distance, you couldn't answer it. Right? You have to have a starting point and an ending point, otherwise you can't get what your delta V is. You could have done from A to B. You'd have a starting point and ending point. So you have to have a starting point and ending point. Questions about this? Yes? Anybody want to ask a question? Isabel? Yes. I was using the Pythagorean theorem. So let's just take this one right here, RA3 or 3A as I called it. This side here was 2 centimeters. This side here was 1 centimeter. So using the Pythagorean theorem, I had the R, I put 1, 3. That should have been I put my labels wrong. R. I see I messed up all over the place. R3A would be square root of 1 centimeter squared, so that's that, plus 2 centimeters squared, that's that. Bueno. Conductors. Yes.
Can I ask?
Yes.
None of these equations have really been on here, or maybe I just haven't been able to find them. The hallmarks haven't been on here, and I'm just confused about what I'm going to do on the test. Yeah, like a ball.
Like which homework assignment was it that we couldn't find like the equations? Even the simple ones, if they weren't on there.
Show me problems. Come to my office, show me problems, and I will help you to identify which equation is on there. Because obviously there's not a lot of point of having an equation sheet if you don't recognize the equations there.
Are we talking about like you guys are talking about like when we're on the exam and we get the equation sheet and
Yeah.
we use that?
So she's taking, the equation sheet is already on Moodle, so she's printed it out. And she's saying that when she was doing the homework, she couldn't find the equations necessary.
Well, like even the equations that we're doing in class, like where are they on here?
I can't. I can show you, but I'll do it in my office where we can sit and point to things. Okay, a conductor. Tell me about a conductor again.
It allows electrons to track.
Okay, electrons can move relatively freely, no energy cost. It's an approximation, but it's pretty close to true. Superconductors, it's much more close. It's a billion times closer to true, roughly. So if you have a conductor that has electrons that are free to move on the inside, if you reach equilibrium, those electrons aren't going to be moving all over the place. They're going to be in equilibrium. So it stands to reason the net force on those has to be zero. Because if the net force wasn't zero, it'd have an acceleration and move. But the force on a charge is QE. So if the net force is zero, what is the electric field? Zero. So the electric field inside of a conductor is always zero. And then on the surface, we talked about, on the surface, the net force needs to be in or out. Well, actually, net force is going to have to be out. If the net force was in, it would move inside, right? So net force needs to be out, which means that the electric field lines need to be vertical on the surface. So if you have a conductor, the electric field inside is zero. Outside, the electric field is the same as for a point charge. Now, this is for a spherical conductor, which is all we're going to worry about. But the voltage is not the same. Because voltage, the energy per charge, depends on the distance it is from charges. And so if you are inside that conductor, you have charge all around you that's adding to the voltage. But the voltage can't change inside the conductor because if the voltage changes, that means you have an electric field. Electric field goes from higher voltage to lower voltage. And so if the electric field is zero, the voltage has to be the same anywhere inside the conductor. So you have a constant voltage inside the conductor, and then this is the same as you'd have for a point charge, which is KQ over R, whereas this was KQ over R squared for the electric field. So the voltage inside the conductor is not necessarily zero, but the electric field is necessarily zero. But the voltage can't be changing inside the conductor because that would imply an electric field. Now we get to biology, which is why Kenny is here. Kenny wanted to see, once again, since it's been over a decade since he took this class, how I talk about the biological aspects of electricity here. So in our body, we have membranes, and those membranes are controlled by electricity. We have nerves. Those nerves are controlled by electricity. So our bodies are running a lot on electricity. Now this here is, I believe, showing the action potential for a nerve. But it actually is pretty much the same when you talk about depolarization and repolarization for other tissues, such as a membrane or a muscle. So the same thing, when you have a signal going down your nerve, like let's say you get poked in the side of the cheek, you feel that. You feel that because the signal went down the nerve, but that signal is actually an electrical signal traveling down the nerve mediated by ionic interactions. So you had electricity flowing down the nerve. And, sorry, Dr. Map, I'm not going to talk about the difference in a myelin sheath and not myelin sheath and the nerve conduction and whatnot. We will just go on to talking about other applications which are much more physicky. Electroencephalograms. Electroencephalograms, they put a whole bunch of conductors all over your skull, and then they measure voltage differences between points. Why? Because your brain is just, in physicist terms, a cluster of nerves. And there's electrical signals going through the parts of the brain that are working. The parts that are kicking it don't have much electrical activity, and so you can measure where electrical activity is going on in the brain, and thus you can measure what's happening in the brain. And just a point of reference, electroencephalographs are not really comfortable because they want to make sure they have good conduction across the skin. So they put a little conducting gel and then they kind of abrade it a little bit to make sure they're going to have good contact. So it's not very comfortable. Because I was in psychology research studies in graduate school, and they wanted to measure our response to pain. And so they measured how the brain responds to pain, and then some people were being hypnotized and seeing if the brain was different and if their verbal response, how much it hurt, was different. Somebody asked on Perusal, what's the difference in ECG and EKG? The difference? German versus English.
That's it?
Mm-hmm.
Uh-huh.
In English, it's an electrocardiogram spelled with a C. In German, it's electrocardiography spelled with a K. And two Ks if you want. There's a K in electrical and electro and a K in cardiography. And so that's the only difference. And so in America, we always use EKG, but we're pretty self-centered and we're like, that doesn't make sense that cardio starts with C and we use K. So we're shifting over to using an English abbreviation. So EKG, you're putting sensors on the body and trying to measure voltage differences to see what's going on with the heart. So here's some pictures to give us reference. So how many people have put things on the heart to sense what's going on? Okay, we got 4. So, which kind did you use, Andy?
12 lead and 4 lead.
You've done both. Yeah. How many people besides Andy have done 12 lead? Really?
We do it in the EMT class.
In my EMT class, we did. Oops, didn't mean to go forward. Meant to try to zoom in. Well, I'm not going to try to zoom in that. We did the one that just had 4. And for those of you who are doing 4, which, like, if you're in an ambulance, that's pretty much what you're going to be doing. Just remember, anatomical positions, you're always looking at a person's body as if you're looking at the person. And so you have the right side is here, which is your left. And you have white on the right, smoke over fire, right? That's how you remember which one goes where. White, red, black. Or, right, excuse me, smoke over fire. White, black, red.
You say like clouds over grass.
Okay, so, we never put that one on. We just never did. We only used 3. I don't know. So, that's the one that I am used to. But this here is a whole lot more. You have 6 on the chest, V1 through 6. This here is the right arm. Then you have also one that's on the left arm. And, well, I have a picture on the next slide. Kidding. for where you put the leads for the 12 lead. And each pair is actually considered a lead. Now let's talk about the heart first. Here's a true picture, or roughly true picture of the heart. And I actually checked with Kenny to make sure, and it turns out his teacher taught him the same thing. Here's the heart. The top halves are the atria. And so you have the right atrium and the left atrium. And then you have the bottom parts of the ventricles. So you have the right ventricle and the left ventricle. That looks almost the same, right? Now the heart is a big muscle. And so those muscles run by electrical activity that starts with the SA node, the sinoatrial node. So the sinoatrial node geographically is not part of the superior vena cava, but somewhere in the vicinity of, gotta change colors, somewhere in the vicinity of here, or here on our picture. And so your body sends a signal to the heart that says it's time to beat. And what happens when that electrical signal gets to the heart? You have muscles that depolarize. The depolarization process, you have charge moving through a membrane, and the result of that depolarization is the muscle contracts. And so you have electrical signals that go through the atria like this. Now, it's a complicated process because this is a three-dimensional object, and you have currents going over that three-dimensional surface. And so it's actually a significant physics problem to try to model the actual flow of the electrical signals. But you have the depolarization, and the signals are collected here, or here on my picture. So this was the SA node. They're connected here at the AV node. AV stands for atrioventricular. Now, I believe God created us. And I believe he created us with redundancy so when things go wrong, we can still live. And so that AV node, what it does is it collects those signals and then it sends them down the bundle of His. The bundle of His being this right here. And His is spelled His. So that's the bundle of His. Awesome what? Band name, yes, it actually would be. Yes, we are the bundle of His. In my picture, that just is this. But what happens if somebody has had some damage to their atrial muscle? Does it depolarize and repolarize right? So that means that muscle is not going to contract. What is that going to do to your efficiency of your heart?
It's going to decrease it considerably.
Decrease it not considerably. You're at least 70% as effective if your atria are dead. That's pretty good, right? Well, no, you're 70%. You've only lost 30%.
Bro, heart muscles.
30% can be a lot, though.
Can't heart muscles or heart muscle cells, can't they
30%.
even if they don't get the signal, they can still generate their own signal?
Well, what happens is if you don't have the signal that comes to the AV node, it waits about 1/40th of a minute and says, we didn't get anything. I can't let this body die, and so it generates its own signal. And so the AV node will keep your heart running at about 40 beats per minute. And of course, the amount varies per person. Even if you're not getting any signal through the atria. Now, of course, if your pulse rate drops into around 40, we might start worrying that you have a problem. And what do we call that? Bradycardia. So if you're Brady, it might be because you have a problem with the signal going, either getting to the SA node or going through the atria. But then you have that signal go through the bundle of His. And when it gets down, after going through the bundle of His, you have all of these things called Purkinje fibers that go into the heart and stimulate the heart to beat. And so, what if you're like my grandma? Oh, it was about a decade ago now. Her heart rate dropped to about 20. She had a grade 3 bundle blockage, which I don't know the different grades of bundle blockage, but that bundle is the bundle of His. And she was not getting an electrical signal through the bundle of His. Hence, there was nothing telling the heart to beat. But the Purkinje fibers, they sit there and they wait about 1/20th of a minute, and they're like, nothing's happening, this body's going to die. And so they send their own signal, so your heart beats about 20 times a minute when you have a bundle blockage, which is just about enough to be conscious, so people often will go in and out of consciousness at that point. So that's a reduced level of consciousness for sure. It's a pretty complicated system, and it's all running on electricity. But that electricity is mediated by, like I said, ions flowing through membranes. And so if you get your sodium-potassium balance off, then you will interfere with that electrical signal. And that is bad. So let's talk about the EKG. What do we call this?
It's a P.
Well, okay, you're going more deep than I meant with my first question. I am going to get there with my second question.
Sorry.
This is a normal sinus rhythm. This is what we like to see. Normal sinus. Has nothing to do with your nose or cavities in your head. The normal sinus rhythm means that you're getting a rhythm as you should, starting with the SA node and working its way through. So now what Claudia was going to answer. This first part. What do we name that? That's the P wave. The P wave is the depolarization of the atria. Depolarization corresponds with the muscle contracting. So that's the atrium pumping blood. Now, if we look at the picture on the right-hand side, we have blood that comes in through the superior and inferior vena cava, or vena cava is what I was taught in high school because, it's the way we pronounce things, and goes into the right atrium. You also have blood that comes in through the pulmonary vein into the left atrium. My EMT teacher was very careful to point out that the pulmonary vein is the only vein in the body that has oxygenated blood, and the pulmonary artery is the only artery in the body with non-oxygenated blood, just in case that's ever important to you. So when you have this P wave occurring, you're having the right atria, this section, and the left atrium, this section, they're compressing, pushing blood through these valves. You have the tricuspid valve. It's basically, I think of it as pieces of rubber, but it's like you have 3 pieces of rubber that come together. And so you can push something through it, but it seals together so it can't flow back. When you have a heart murmur, stuff is flowing back through one of those valves. You have, on the left side, you have the bicuspid or mitral valve. It only has 2, so it's like this instead of 3. So you're pushing blood through there when you have the P wave, when you have the depolarization of the atria. So then we have the next part. And the next part, especially in class of this level, we don't disambiguate. We just call it the QRS complex. It's a complex because it's more than one wave. It's 3 that are all occurring at roughly the same time. So what do you suppose happens next after you have pushed blood through the atria, or through the valves from the atrium into the ventricles? Okay, so the ventricles are now depolarizing. And the QRS complex, part of that is the ventricles depolarizing, giving you a big spike. But you also are having recovery or repolarization of the atria. So the recovery of the atria is occurring the same time that the ventricles are pumping blood through the body. And of course, when I say pumping blood through the body, what's the right ventricle doing? Pumping blood to the lungs. The left ventricle is pumping blood through the rest of the body. So the right ventricle, it actually should have a low blood pressure. It should be on the on the ballpark of 25 millimeters of mercury. Now, you guys don't know, probably, but about 14 years ago, I had pulmonary emboli, which means I had blood clots blocking flow of blood through my lungs. And so, what was that? Okay. So the blood pressure in the right ventricle was 90 millimeters of mercury, way above what it's supposed to be. And so they were very worried that I would have a heart attack because the right side of your heart is not muscular. Okay. The left side, that's the muscular part, pumping blood through the body. Both of the ventricles are going at the same time. Purkinje fibers cause it to happen. Yes.
Sorry, it's like related, but like a little more in depth. So, because we have like pulmonary embolisms and then we have like general embolisms.
PEs.
But like it's interesting. Is it? Sorry, this is gonna be dumb. But like, is it because like the heart goes directly to the lungs, but we have a specific name for pulmonary embolism? We talked about that a lot because it occurs more often.
Yes, PEs occur a lot because anytime you have a blood clot that forms in the body, it comes to the heart and goes first to the lungs, and the lungs kind of act as a filter, which kept, I would have stroked out if it wasn't for the lungs, right? But the lungs kept the blood clots there instead of them going through the rest of the body.
Because you can have like embolism in like different places, but we don't have like a name for like one in your arm. Huh? Sorry.
Yeah.
I just thought that was
It's a PE because that's where it gets lodged. Okay, so back to this. We have one final piece of this normal sinus rhythm. So what do you suppose we call this last one? That's the T wave. And the T wave, we have depolarized the atria with the Q. We have repolarized the atria and depolarized the ventricle with the, I said Q, said P, with the QRS complex. And so what's left for the T wave to be? That's repolarization of the ventricle. That's the main part of the heart recovering so it can pump again. So that's a normal sinus rhythm. What's this? All I know is this is death. My EMT teacher said when you have electrical signal like that, the heart is quivering. It has no coordinated action. And so you have this part contracts, this part contracts, this part contracts, this part. There's nothing coordinated. You're not actually moving blood. And so that is, if that's what's happening, then you have a dysrhythmia or fibrillation, and you are not causing blood to be oxygenated or pumped through the body, which means that you are going to die in a very short time, or as he said, circling the drain of life. Yes?
ventricular fibrillation? What is it? I mean, people in this class know. The one that an AED catches.
It couldn't be that.
Okay.
VPIP, right? Yeah, VPIP.
I do not remember which are shockable and which are non-shockable rhythms, but some you can correct with shocking, some you can't. Let's talk about the shocking. So why was I spending all this time on biology, on the heart working?
Because it works. I mean, you need like the electrical impulses work.
Right. It's all based on electricity, and we are mapping this by looking at the voltage difference between one part of the heart and another. Here is actually where you put the lead, so right arm, right leg, left leg, and then the 6 on the chest. And depending on which two you compare or which ones you compare, you can see the voltage difference in different directions. And so this here is a 12 lead read, and they get different information because you're looking at different angles. Yeah.
A little off topic, the slide before also had a V4R that I haven't seen before.
This here?
Anything about
That
what's wrong?
I think that is just supposed to be the right arm one. That's what I think.
Oh, okay.
Okay, so last thing is about shocking. As mentioned, I think before class, they took away our defibrillators that gave us a readout, so we wouldn't have to try to determine if it was a shockable rhythm. And the machine would just say, no shock or shock. And when you shock the heart, you're putting a really large voltage across the heart. What that's going to do is force the muscle to depolarize. And so basically you're forcing the heart to go, and it all contracts at once. And then what's going to happen? Ideally, what should happen? After it depolarizes, what should happen next?
It starts again with a normal.
Okay, it should repolarize. And so the goal of shocking is to stop the heart. You stop the heart and you hope that it starts up right.
Right.
And as anyone who's worked with this knows, you really have three outcomes that can occur. Outcome number one is it just continues on with what it was doing before. Outcome number two is it shifts to a new rhythm. That new rhythm might be more compatible with life or less compatible with life. Option number three is it might decide not to restart. In all cases, you've basically killed the patient and you're hoping they come back to life. And if they come back to life, that it's in a manner that's more compatible with consistent living. So you don't want to be shocked, but if that's the only hope, that's what you do. All right, have a great day. I'll see you for lab tomorrow.